This is lecture 11C for Calculus 2 on using the terms of the series to test for convergence and also on absolute and conditional convergence. In this lecture, I'm just going to go over some of the tools, some of the tests that are used on the terms of the series to determine if it converges or diverges. Basically, though, what you have to do is just start doing some of them. In the homework, I tried to give you hints on how to work them out, then go back to the examples in the book and the examples here. I don't think it'd be beneficial for me to go over example after example. This would make these lectures very, very long. So this is just to give you the vocabulary. I think you should watch. It's just the idea to get the vocabulary, ratio test, root test, kind of get the idea of those, and then start working some problems. And be sure to ask me about them in the recitation sections or to send me an email. Because so I'm going to go through some of the tests using the terms of the series AN. Okay. One is this comparison test. All right. So the idea is that you have two sequences. They both have non-negative terms. Terms could be 0, but they cannot be negative. All right. And so I'm going to call one a to the n and the other b to the n. And I'm going to look at the associated series. And what I'm going to require first is that at each value of n, a to the n is less than or equal to b to the n. So b to the n sort of dominates a to the n, and they're both positive. Now we have this result here. If the bigger one, if b to the n converges, then a to the n also converges. So if the larger one converges, it sort of drives the smaller one to convergence as well. On the other hand, if the smaller one diverges, then the larger one has no choice but to be divergent as well. Right? So this is your comparison test. If you can find another series in which all the terms are greater than your series and that bigger one converges, then you know that your series converges as well. The next test really starts out as being an observation and fails to be a test. It's a nice observation, but it doesn't really help you. And this observation is that if you have a series that converges, then the limit of the terms, a to the n, the limit of the sequence that you're summing, the limit of those terms is 0. That's just an observation. So if you have a series that converges, then the terms a to the n converge to 0. Right? And again, this is a property of the convergent series. It's not a test. In other words, if you had a series and the terms of it converge to 0, the terms of it here, what I'm saying is this holds. Right here, this holds. Does not imply that the series converges. So what we have here is a situation like this. We have a to the n converges, implies that the limit as n goes to infinity of the terms a to the n is 0. That arrow only points in this direction. It does not point this way. Because the terms go to 0 does not imply that the series converges. On the other hand, if the terms do not go to 0, then the series diverges. So, in a sense, you can use it as a divergence test, but you cannot use it as a convergence test. So here is the nth term divergence test. If the limit, as n goes to infinity, of the terms a to the n do not go to 0, if that limit is not 0, then the series diverges. The ratio test is very useful. It's used later for power series, to test the convergence of power series. The ratio test looks at the terms a to the n of this infinite series. First, it requires they all be non-negative. That means they can be 0, positive, but they cannot be negative. Okay. And if they happen to be negative, you need to take the absolute value and test for absolute convergence. So the ratio test, what it does is show that the sequence is monotone or not, and bounded or not. Right. So here we have the ratio, a to the n plus 1 over to the previous a to the n. Take the limit as n goes to infinity. In this case, we're only looking at adjacent terms. Right? A to the n plus 1 over a to the n, and we look at the limit. Now, just because it has a limit does not mean that it converges, right? If that limit is less than 1, then the associated series converges. Right? If the limit is equal to 1, the test is inconclusive and you have to go use a different test to figure it out. If that limit is greater than 1, then the series diverges. So you look at the ratio of adjacent terms and take the limit. Whatever that limit is, you test it according to this criteria. If it's less than 1, the series converges. If it's equal to 1, the test is inconclusive and you don't know if the series converges or diverges. And if it is greater than 1, then the series diverges. That's your ratio test. Again, if the terms are negative, take the absolute value and apply this ratio test and test for absolute convergence. And if it converges absolutely, then you know it does converge. The Writ test, I haven't used that as much as the ratio test. But here's the Writ test. It looks very similar to the ratio test. Again, you're dealing with the terms of the series A sub n. And it requires that these terms be non-negative eventually. In other words, the first couple of them could be negative, but then after a while they have to be positive from then on in. All right, in this ratio test, you take the nth root of the nth term, and you look at the limit as n goes to infinity. Right, here's that limit L. And then the conditions are the same as for the ratio test. If L is less than 1, the associated series converges. If L is equal to 1, the test is inconclusive. If L is greater than 1, then the associated series diverges. Here's the alternating series test. Now this is applied to a series in which the terms alternate in sign. Plus, minus, etc. All right. Here's two examples. Minus 1 to the nth power, that will alternate in sign. Minus 1 to the n minus 1, that alternates in sign as well. Okay. It's just that one starts positive, one starts negative. Now the series, here's the criteria for this. Again, there's 3 criteria, but it's different from the Writ and the ratio test. The series converges if all of the 3 following conditions hold. The terms have to be positive. That is all. The b to the n has to be greater than 0. The alternating part, in other words, just has to do with some multiplier. Okay. The sequence is non-increasing. Non-increasing means it's monotone decreasing. The next term is less than or equal to the previous term. Right. And then the sequence of these terms converges to 0. If all those criteria hold, then we know that the associated series converges. That's the alternating series test. And now I want to make a few remarks about absolute and conditional convergence. Here's the definition. A series converges absolutely if the absolute value of its terms converges. Right. In that case, the series itself converges because absolute convergence implies convergence. Now a series converges conditionally if the original series, just n equal 1 to infinity of a to the n, if that converges, but the absolute value of the terms does not converge. That's called conditional convergence. And the absolute convergence test, of course, says that if the series converges absolutely, then the series also converges. And here's the interesting result. If the series converges absolutely, then the terms can be arranged in any way. The limit of the rearranged terms will also converge to the same limit. That's with absolute convergence. Now if the series converges conditionally, then if you rearrange the terms, this can cause the series to diverge or to converge to any real number. And there's a special mechanism on how to do that. If you want it to converge to 60, first you place enough terms initially so that you get just a little bit over 60, then you put a term or two so you bring it down below 60, and you can alternate like that, converging to 60. Say the original sequence converged conditionally to 10, but you can use, by manipulating the order of the terms, you can make it converge to any real number or even to diverge. That is quite interesting. So absolute convergence implies convergence. Conditional convergence means that the original series converges, but the absolute, it does not converge absolutely. And that is just a rundown of the different methods for testing the convergence of series. I tried to organize them and pull out the most important things, sort of separate them out for you so you can see them. There's a lot of words in the textbooks. Go read all those words. But just to keep the different tests separate, I've kind of put them here in this list. And then, of course, there are many examples in the homework for you to work out.